Thank you for viewing our educational videos on micromanufacturing with lasers. In Part 5, Dr. Ronald Schaefer, CEO of Photo Machining, will discuss applications in the aerospace industry, battery manufacturing, and cutting CVD diamond. Over to you, Ron.
Thank you, Rick. So, we've talked about medical applications, we've talked about microelectronic applications. Let's talk about some aerospace applications. Aerospace applications are typically fairly high value, fairly low yield parts. Many times they're prototyping. For instance, if a satellite is going to Mars, for instance, we may only need one part, but that part better be perfect and it better work. And there may be tens or hundreds or thousands of parts made up to that time with different parameters that are prototyped so that when they put that part on the satellite or the Mars lander or whatever, that part actually works correctly. So in general, the yield, the final yield is fairly low, but the cost or the value for these parts is generally pretty high. One of the applications area that's been around for a long time is marking of aircraft wire. And this is done with primarily UV lasers. The reason is that aircraft wire is generally made out of Teflon for whatever reasons in the aerospace industry that they need to make these things out of. And Teflon doesn't mark very well, certainly not with ink or printing pads. And so lasers mark Teflon extremely well. They can also be used for high resolution wire stripping. We can also use lasers to generate flight panels. Many of the flight panels that you see in aircraft cockpits have some sort of a thin film like ITO over it, and so these things are then patterned in a resistive kind of pattern so that a small amount of heat can be applied to the actual flight panel to keep it at a constant temperature and therefore assure that it functions correctly. Aircraft engines. This is again another huge area for laser technology. The holes that are drilled are typically about 1 millimeter in diameter, which puts it still within our micromachining, but at the higher end of the feature size. These holes are usually drilled in the metallic parts, typically aluminum, sometimes titanium. They're typically used for cooling and airflow and also for flow dynamics, although there are a couple of different other materials that are sometimes looked at. The first one is thermal barrier coatings, and the removal of thermal barrier coatings or the laser drilling or cutting of the thermal barrier coatings. These are typically zirconia ceramics that are put over the metal parts to stabilize the thermal conditions. The other material that we see a lot of in the aerospace field and in other fields as time goes on is the drilling and processing of carbon fiber epoxies. And in the aircraft industry, these are used as spoilers for noise reduction, but they're also being used for many different other applications. For instance, the heads of golf clubs, for bicycles, for, in some cases, aircraft bodies and engine body components. So there's a very, very big interest in the processing and the laser processing especially of these carbon fiber epoxies for the next generation aerospace kind of devices. Lasers and battery manufacturing. As I said earlier, battery manufacturing is a very good area, a fruitful area for lasers because, first of all, it requires high precision. Secondly, lots and lots of batteries are being made these days, not just for automobiles, but for everything you can think of. And third, because in many cases, the really good batteries have dissimilar materials that need to be joined. So we use lasers for actually cutting the electrodes. Has to be fairly high speed, has to be fairly accurate, and has to deal with refractive materials in general. We use it for many different joining applications like sealing the battery housing, joining of dissimilar materials inside of the batteries, joining of internal components to the electrodes and the terminals, and so on. CVD diamond is another interesting material because there are very few options on how to cut it or drill it or process it. Diamond is the hardest material, so mechanical techniques really don't work very well with diamond. And even techniques such as EDM don't work. So lasers are a good candidate. And it turns out that we can cut diamond, because it's carbon, with almost any laser. Unfortunately, if you use a CO2 laser or a long wavelength laser, you're going to get a lot of charring and carbonization. The diamond reverts back to its carbon form. So that's not really an option, but if you start at 1 micron, you can make very good cuts with a 1 micron infrared laser, as you can see in the screen in the middle. That was cut with a 1 micron fiber laser, fairly fast cutting and fairly good quality. You can see that there is a little bit of carbonization around the edges, but in some applications that's acceptable. In other applications, that might not be acceptable, and so on the left-hand side, you see diamond that was cut with a 248 nanometer UV laser. In this case, we don't see any evidence of microcracking, microchipping, or carbonization. So in principle, this thing with a very minimal cleaning can be used for applications such as, for instance, heat transfer. In this case, if you've got any carbon between the diamond and the heat generating source, you're not going to have a good heat transfer. So you really want to have diamond butting up against your heat source. On the right-hand side, again, we see another piece of diamond that was cut with a 524 nanometer laser. And basically, this cutting also shows really no signs of carbonization, microcracking, or any negative effects. Some more pictures of CVD diamond. This actually is a freestanding diamond screen made with a 1 micron fiber laser. The actual parts that we cut for the customer were the squares that were taken out, and this freestanding screen was what's left over. So the squares are about 5.3 millimeters on a side, and the ribs are about 150 microns wide, and on the order of a couple hundred microns in thickness. So you can see we've still got a lot of mechanical stability there, even though the feature sizes are extremely small. Another application for diamond drilling is the making of diamond anvils. Diamond anvils are used in scientific experiments to generate conditions that are sort of like in the interior of stars. Very high pressure, very high temperature. And the only way that this can be done is by using diamond anvils and putting a lot of pressure on the substrate chamber or the sample chamber that's laser drilled into the end of the diamond using primarily UV lasers. So here's this carbon fiber reinforced polymer that I was talking about earlier. This shows what happens when you drill it with many different kinds of lasers, and these are all taken directly off the laser, so they show some signs of debris and some signs of heat effect depending on the laser that we're talking about. But we can also do a very good clean job drilling these carbon reinforced polymers. On the left we see 1 millimeter diameter holes and 1 millimeter thick carbon fiber reinforced polymer, and that was drilled with a 1 micron fiber laser. On the right hand side you see 30 micron wide freestanding ribs, also cut out of the same material, but this time using an ultra short pulse laser. This is the 355 nanometer 10 picosecond pulse length laser, and these ribs were left standing and intact, and the rib diameter, like I said, is about 30 microns wide. Alumina is another very good material for working with. It's commonly used in many different applications, especially in the medical and also the electronics areas, sometimes in the semiconductor areas. In the middle you see a semiconductor probe, in the middle of which are drilled about 1,000 different holes. And those holes were drilled with a UV laser. On the right hand side of the screen you can see approximately a 4 mil diameter hole. It's about 4.2 mils at the top, 3.8 mils at the bottom. And by the way, 4 mils is about 100 microns if you like the metric system. And this was drilled through over 1 millimeter thick ceramic. So we kept a fairly high aspect ratio throughout that whole drilling process. And this is very important when you talk about applications such as probe testing, because wires are stuck down in those holes. And if the holes are too large, the wires will wobble around and you won't get a good contact. And if they're too small, well, you just can't get the wire in. So the holes have to be very precisely manufactured with a fairly low aspect ratio. On the lower left-hand side of your screen, you'll see what essentially looks like a miniature meat tenderizer. So if you look at this thing, it will show very small pyramids on a flat surface. And those pyramids look like the surface of a meat tenderizer that you'd find in your kitchen, only much, much smaller and done in alumina rather than wood.
Thank you, Ron. In Part 6, Ron will review the relative merits of outsourcing laser micromanufacturing versus using an in-house laser system. Visit photomachining.com for more information. Thank you.